Hey, Diana, can you hear me?
I can hear you.
Okay.
I'm sorry, I didn't know that Anand had this on a automatic open up at 5 before the hour.
Okay. So Diana, is that possible? I can ask my research PhD student assistant to also join here.
Yeah, that's fine.
Yeah, how she can join? You send her
It's
the
the
same link?
same, it's the same link. I don't, she just has to register and then
Okay.
I can, but unfortunately I need Anand to be able to
Okay, she is here.
okay, can you share your screen?
Yes, looks like I click, I can.
Oh,
Wenjing, can you also, I also ask my student, are you able to share screen, Wenjing, if you click share?
So you mean I share the slides for the
Are you able to share?
yeah, oh, I will try.
all right. That looks like it's gonna work.
Yes.
Okay.
Then I will bring my student to co-present with me. The reason is I know how it's conceptualized, but if we go to detailed coding, certainly students they are in the frontier of really get it implemented. So
It's
I
all
want,
right. It's
yeah.
okay. I get it. I get it. We'll make sure that her name's on the presentation as well.
Yes, I put her as a first author there. So yeah, her name is there.
Okay.
Mhm.
So yeah, all of the Zoom is based at University of Illinois,
Mhm.
and I don't have access to any of the I can't control anything. So I probably it's set for, I'm guessing it's set to have other people only allowed in. Oh, good. Anand's here.
Yeah, Anand here. Hey, Anand.
So Anand, are there is it set so that people don't join till the top of the hour? It seemed like it opened up automatically at 5 of.
Yes, I did set it up to open at 5 before, but anyone can join at that time.
Okay. So how
So
many
just
people registered? I'm sure that we had more than 0 registrants.
Definitely. Let me. 32.
Hey,
Yeah.
Song. Hey, Song, how is everything?
Oh, hi. Yeah.
Okay. So Anand, are you able to stay on for this hour?
Yeah, I'll be on.
If you're not, let me know. I can. I'm just trying to balance
Yep.
other things right now.
Yeah, I'll stay on for that.
So Shinoy's Wenjing is one of his PhD students, and she's also going to be sharing her screen.
Yes, I will ask
5 o'clock.
Wenjing to share screen. Then
Okay.
after I give the more background introduction, how it can conceptualize, I will let Wenjing to take over to further present. The reason is Wenjing is our student leader in implementing the code. So it's also give her the opportunity to present.
Right.
Great, no problem.
Okay, now it's 11. So should we let Wenjing to turn on the video and share screen?
No, we should wait. People are still going to join in the next couple of minutes.
Okay, let's give them another 5 minutes also.
Yeah, couple
Yeah.
minutes.
Yeah, a couple minutes usually. So Anand, I'm gonna have a whole bunch of, stay tuned for an email from me because we have to catch up on a few different things after this.
Yep.
Hi, everybody. Thank you for joining us. We're going to get started in just a minute as people continue to log on for today's VCO. As a reminder, please keep your microphones muted until we have some opportunity for question and answer. But if you have questions that come up before, please feel free to type them into the chat, and we'll make sure that there's time at the end of the presentation for some presentations. I mean, for some questions. Okay. Anand, do you want me to, I'm gonna turn it over to you now.
Yeah.
All right,
Yeah.
thank you.
Yeah, thank you. Hello, everyone. My name is Anand Padmanabhan. I'm a research associate professor in the Department of Geography and GI Science at the University of Illinois Urbana-Champaign. And for iGuide, I serve as managing director. And iGuide stands for the Institute of Geospatial Understanding through an Integrative Discovery Environment. And we run this almost weekly series called the VCO, or the Virtual Consulting Office, where we share some of the stuff that is happening within iGuide, as well as kind of community participants and our collaborators share their work. Today, I guess our work is being shared by Xinye, and he is from Texas A&M, and he's also a UCGIS iGuide community champion, and they have been doing a lot of work on the broad area of geospatial AI. Specifically, I guess the talk today will be focusing on digital twin framework for spatial temporal vision transformers for heat resilience. So with that, maybe I'll pass it on to Injay, and I guess you have a student as well who'll be presenting with you, right, Injay?
Yeah, thank you. Thank you, Anand, Diana, and everyone. And it's a good morning from College Station, Texas A&M, and I'm Xinye Ye. Currently, I direct the Center for Geospatial Sciences, Application, and Technology at A&M. I'm a full professor in urban planning. I also hold a joint position in geography and computer science. So today I will co-present it with my PhD student Wenjing Gong, and Wenjing can share screen. I will go through the slides. Wenjing, can you share screen so we can get things started? I will go through the more about the background of the project, how it is, and how was our future plan, and for the more detailed coding implementation. Since Wenjing is our student leader, I will let her to go through that for those parts. Wenjing, can you share screen?
Okay.
Yeah. So while Wenjing is sharing screen, Wenjing can Wenjing, can you make it full screen? Are you able? Oh yes. Okay. So this project itself, firstly, thanks a lot for the support from iGuide. At the same time, it's also relevant to our NSF project and NASA, and as well as the support from A&M campus. So reason is, if you have visited Texas A&M during the summer time, you will know it's extremely hot outside. And within the higher frequency of extreme weather, there's a big concern is students staff, faculties get more exposed to like the overheating as an issue. So now why we, next slide. Next slide. Why we need to prepare for the hotter temperature? Most of the literature talk about we need to deal with the extreme heat in the in different communities, especially urban communities. However, we want to point out the campus is a very different situation because the same rising extreme heat issues will also emerge in the campus area. However, if you are in the downtown, though it's overheated outside, but you might have the since many business open doors, you can quickly get in to enjoy the air conditioning or the other, right? There's many doors you can let you get in. Traditional educational buildings are not set like this. They have limited entrance kind of doors. As well, they usually have a big green space and make the kind of the students or faculty staff is very easily get exposed to the very kind of insufficient cooling infrastructure. So these complexities highlight the real need for some tailored heat assessment models to inform campus-specific mitigation strategies. Next. So so for that, we have put this kind of solution under what we call the urban digital twin. Right? It's a very promising solution for mitigating extreme heat exposure on campuses by providing virtual replicas that simulate and manage the built environment. Why we talk about simulate is because we need to simulate both the atmospheric dynamics, and we also need to simulate if human beings carried out some mitigation strategies. For example, in the landscaping, or you are building more like plant more trees or different types of trees, and bring in different levels of the artificial and the human, like natural, like the shadows. Next. Okay, so certainly when we talk about all the greater potentials, the limitations exist. Firstly, the computational limitation. Wenjing will go into later is about the very high computational costs and resource demands if you want to do this. And since many times for the if it's outside, it's very overheating. We need to make a decision as soon as possible. Is we stay indoors or we avoid going outside. We need immediate decision making. We don't want to wait for very slow simulations outcome. At the same time, is we don't want to always visualize what has happened, right? What happened previously is interesting, but more importantly is what will be the next minute, what will be tomorrow, what will it be in a specific site, or how if I go from one place to the other place on campus, how much overheating I need suffer from. Next. So if we want to make the climate digital twin fully function, we also need to consider we need to integrate the data and the model. On one side, if you look at bottom right, is the multimodal data integration is a big challenging issue, especially if we consider the complex spatial temporal dependence among these data sets. And at the same time, overheating itself is not only about a measurement of temperature or something we measured from our app or sensor. Behind that is a complicated atmospheric dynamics. So we also need to have the knowledge about how we capture the nonlinear and non-stationary atmospheric kind of dynamics. Next. So we are building this kind of a conceptual framework. Wenjing, now it's your time. Talk about how we are doing this.
Okay, so this is This is the study's conceptual framework, and it mainly has these 5 sections. So we begin with the collection of spatial and meteorological data to establish the foundational data layer. And then we used a physically based human hysterex simulation model to simulate the meridian temperature, and further we calculate a climate index called the UTCI, which can indicate the human heat exposure. And then next we analyze the spatial temporal variations of the human hysterex. And the next is our main contribution. It is we further developed a data-driven deep learning model, and that is the spatial-temporal vision transformer model, which combine the first 2 sections results to make fast predictions. And finally, we apply this data-driven model to a digital twin application, which can transform the theoretical analysis into practical extreme heat response strategies. Next I will introduce the data set. So the spatial data is at a 1 meter resolution. It was initially from the LiDAR point cloud, building footprint and land cover. Then we generate the digital elevation and building height model, and we use the point CN model to classify the tree points in the LiDAR point cloud, and we further generate the tree height model. And for the meteorological data is at 1 hour resolution. It includes the observation data and radiation data. They were all from the public data sources. So then we use the Solvik model, a physically based climate model, to simulate the 24-hourly mean reading temperature maps for the 14 days. So the 14 days is we calculate the heat wave days in 2022, and we also add 3 days before and 3 days after the heat wave period to make a comparison. So for the simulation period, it is overall 14 days. And we further developed a custom script to generate the UTCI maps for the whole study area, because the physical model cannot generate the maps for the whole area. So then they developed the ST-ViT model to enable rapid forecasting. So for the input data, we followed the physical climate model's input requirements, but we excluded the variables require high computational pre-processing, like the sky view factors. For the data pre-processing, both spatial and temporal data were normalized for model training, and the predicted UTCI maps were denormalized for interpretability. And for the prediction setup, we used 336 hourly time steps. We predict the UTCI maps for the next 24 hours based on the previous 24 hours. We also test different sliding window tabs to evaluate the model sensitivity. So for the model architecture, it is a transformer-based decoder-only architecture, which is designed to spatial temporal dependency modeling. I will introduce the model architecture later. And it has 3 parallel attention mechanisms. 1, spatial attention, which can capture the spatial relationships, and 2, temporal attention can capture the long-term dependencies of hysterex and meteorological features. And then both the spatial and temporal data were merged through the additive mechanisms. And for the output, a unified representation through final linear projection, which can preserve both spatial and temporal resolutions. So we also compared the ST-ViT model with two benchmark models, CN plus STM and UNet plus ASTM, which these two models are commonly used for spatial temporal prediction. We chose three evaluation metrics, and on the right side are some model implementations. All the models were built using Python with PyTorch, and we trained this model on two high-performance GPUs. We use the MSE loss as the loss function, and we use the Adam optimizer with a learning rate of 0.0001, and we also use early stopping to prevent overfitting. So prediction model database was then constructed based on our previous data set and the physical models simulation results. And so these results are input into the data-driven model. So for the results, we evaluate the performance of the deep learning models across various time steps. We found the ST-ViT model outperformed the another two baseline models across all metrics. Additionally, we also evaluate the computational efficiency of the ST-ViT model. We found this model can exhibit real-time capabilities. It predicts a 1200 multiplied 1200 pixels image in about 7 seconds, and it is 16 times faster than our previous physical climbing model, which is a QGIS plugin. And when considered the physical climbing model's pre-processing procedure, it is our data-driven model is more than 600 times faster. So the ST-ViT model's performance was then validated against the physical model results. We analyzed the UTCI variations across typical campus areas on July 15th at 4 time intervals. We found that both models can capture urban morphology effects on the human hystrax, and but we found the nighttime predictions showed a strong agreement, but the daytime had a relatively larger discrepancies. We found it overestimated the human hystrax in vegetation and the shade areas, which indicated some limitation in capturing the localized cooling effects. And we also found this model has most extreme values. You can see from the right columns graph. It has a narrow distributions and concentrated peaks. We also evaluate the prediction model performance temporally. We found it also has a strong temporal dependency in the model areas. So we found the MAE peaking at noon and lowest between 2 and 6 p.m. We also found the tree cover areas have the largest areas, and the water surfaces have the smallest. And the paved surfaces and grass follow the overall MAE trend. So this is our application. It is provide an interactive web-based interface that incorporates previous model and analysis. So I will quickly introduce this four components. So the A part is a summary view, which can enable users to adjust time to analyze the dynamic human hystrax changes. And the B part is the photorealistic 3D tiles map. It visualizes the spatial distribution of the UTCI at a high resolution of 1 meter using the color-coded heat maps to display thermal outputs. And the C part is the region selection function, which can allow users to select specific areas for the data-driven powered simulations, which can enable a specific analysis for the user-defined scenarios. And lastly is the path recommendation module, which can generate optimized working rules with the average UTCI values based on the user-defined origins and destinations. So together, these modules can create a highly interactive interface that supports decision making. So next, I will introduce the dataset and code that we uploaded to the iGuide platform. So for the dataset, we uploaded all the needed training datasets, including the weather data in the ST-ViT file, and the spatial data and the simulated UTCI images. And these data are about 20 GB. So it is a large data set. The weather data includes these 7 features in the 336 time steps. It is hourly data for the 14 days. And the spatial images include 4 urban features in the GeoTIFF format, including the building height model, digital elevation model, tree height model, and the land cover maps. So then the output folder includes the simulated UTCI map results. It is also a sequence mappings. So these GeoTIFF images you can see from the right, it is a plotted example. So for the code, we also uploaded, we mainly uploaded the training and evaluation section for the ST-ViT model. I will first introduce the custom dataset for the spatial-temporal data processing and how the multimodal data were organized and input to the deep learning model. And then I will introduce the model architecture, how we construct the spatial-temporal transformer model. We all know that the traditional ViT model is used for the classification task, but in this study, we modified the model to do the image prediction task. And then we will briefly introduce the training and elevation process. So we put all the code on a single Jupyter Notebook file in the platform, but in the real world training process, these code sections were usually separated in different Python file. And also something we would like to note is the model was trained needs a high performance GPU, so it cannot directly run in the platform. But if you want to if you are interested, you can download this data and codes. And if you are doing your own research, you can upload updated data folder with your own data sets in your study area. And if all the data structures are the same, you can directly use the code to train your own model. And definitely, you can also optimize the model and training process. So for the first step, we defined a custom dataset that inherits from the dataset-based class, which is specifically designed to process 3 types of data. And this data were loaded and were aligned temporally and spatially, then packaged into the tensor structures with precise dimensions that preserve both the spatial relationships and the temporal sequences, which are needed for the transformer architecture to effectively learn the spatial temporal patterns. And for the model, we first defined a tension layer class that inherits from the NN module, which implement a multi-head attention mechanisms designed to handle the inputs with additional dimensions by supporting the attention over any specific dimension with appropriate reshaping for extra spatial temporal features. So this code defines a self-attention layer class that also inherits from the N module. Implement a standard transformer block with self-attention, residual connections, and a layer normalization, and also a feed-forward network. We then defined a cross-attention layer class that implement cross-attention mechanisms that allows one sequence to attend to another, commonly used in decoder to encoder attention within the encoder-decoder architectures. So this code define a decoder layer class, implement a transformer decoder layer with masked self-attention and cross-attention components used in sequence-to-sequence models to generate output while attending to encoder output. So finally, this code defines a spatiotemporal transformer decoder class that implement a decoder-only architecture that process both the spatial and temporal inputs using the separate attention mechanisms, then combine them for the prediction. And for the training process, we define a function named split data set by time that divides the data set into the training and validation sets based on the temporal sequence. It can maintain the time order instead of using random splitting, which is crucial for time series forecasting. And then we define an array swapping class that implements mechanisms to prevent overfitting during the training by halting the process when the validation loss stops, improving for a specific number of epochs. In the evaluation process, we converted the normalized values output by the model back to the original UTCI value range. We saved each pixel's prediction and ground truth value to a CSV file. Finally, we calculate the accuracy metrics, MAP, MAE, and RMSE from the prediction results CSV file. And the detailed evaluation results were introduced in the previous slides. Yes, so that's all my introduced. Thank you.
Thank you. Thank you, Wenjing, for the presentation. So we can take a questions from the audience here. Any questions, comments? So
Hello.
okay.
Hi, I have a quick question. So how does this, I guess, have you looked at applying this for a larger area or smaller area? How does that, how do the methods adapt to variations?
Wenjing, do you want to take the question?
We currently apply this framework and models only in our Texas A&M campus. We have not evaluated it on a large areas.
Oh,
Yes.
A&M campus by size is already very large. It's almost like a mid-sized city, the downtown.
Mm-hmm. So I guess I'm wondering, so to scale it up or down, is there
guess,
anything, is there more work that you need to do, or it's just totally depend on the data you use?
I would say is since A&M by the size is almost like a mid-sized city downtown size. For A&M, it has over 80,000 students, very large. So the frequent activities. So I would say that now, if we want to scale up, now maybe the major bottleneck is computing resources.
Mhm, mhm. The other question I was pondering, so do you consider the humans in the city? How is that done, or you decide that's not a major factor?
Yes, that's a good question, because we have some ongoing research. It seems different people, human beings with different health conditions, they will treat the overheating differently. For some, they would avoid to have some direct sunshine for a while. They will feel dizzy, or they will always look for other shading areas, change their mobility path, or it will immediately decide how long they can stay outside for how many minutes. So yes, we do have another group, other students working on, is based on the work in this framework, the outcome. This is only showing you how meter by meter, hour by hour, how the overheating stress is. But the same overheating stress will play differently upon different groups of people based on their health conditions.
Thank you.
Thank you. While other people, if you have some more questions, I also want to tell you another interesting thing we are doing. We have another ongoing NS project relevant, but is about in San Antonio. Someone might have traveled to San Antonio. It's a beautiful, have the river walk, a beautiful large city. We work with some local low-income communities to help them to remodel their house for the overheating. Now we are talking about overheating, the outdoors overheating. But when it's really warm season comes, and not only people will mainly stay indoors. However, for these the low-income communities, the air condition does not function well. Even you stay inside, you will also have the overheating stress inside. So we are working with those communities, put the sensors indoors and certainly sensors outdoors, allowing us to monitor the heating stress. At the same time, we have the building some new tools to allowing the local residents to do it themselves, how they remodel their building. For example, they might need to do a little bit the building materials updates. Will help them to mitigate the kind of overheating things. All right. So for that, we bring the knowledge of construction science. That's what we are working on. At the same time, we also pay attention to the many parking lots in large cities. In the large cities, we find out that people are reluctant to go for the public transit. They don't want to have the car share ride. The reason is there's so few canopies around the parking lot. It's a very burning experience if you walk to the parking lot to get your vehicle or drive from there. So we are also working with our agri-life service department, who are mainly take care of many tree species management, or these tree planting. So work with them to model, say how well we plant the trees, what kind of trees will enhance people's kind of make them feel much better to walk during the extreme hot seasons. So all these could become kind of the applications of this research. Thank you.
Can I ask a question?
Mhm.
Yeah, so I have two questions. The first one is about the model and the tool that you use. I think that what you call twin city kind of digitalized approach, I think is very practical and applicable, especially for the small city in the US. So my first question is, with this model, particularly, what is the regular maintenance or frequently update you have to do? How often you have to do it? And my second one, more to the side of applicable, as one of the participant asked earlier, but I would like to learn more about what is the cost associated with develop this tool apply for small city across the US. You know, right now in many small city, the planning department who in charge of so many work, but the staff numbers still small. And I can see the potential to use this kind of digital twin application to help not only maintain the urban management work, but also, do it effectively and hopefully, cost effectively. So I don't know, is that too long, but I would
No,
really
it's a
appreciate if
great
you.
question.
Yeah.
Yes, for the technical details, Wenjing, do you want to answer first? Right, the cost or how costly are we maintaining this model? If
Yes,
we
and how
how
often you
we-
have to maintain it. Yeah.
Yes, and if we, for example, since we use Texas A&M campus as a case, the reason is use campus is students are very much vulnerable in the campus. You will see during the busy semester and busy hours, the students walk around on campus. There's no it's very much you get exposed to all these overheating stress outdoors. So I guess there's a question is some other universities say, hey, I also want to develop a similar one on our own campus. Then how costly it will be, Wenjing?
So I think our digital twin is developed on a web-based interface. Let me see. The oh yes, so we it was deployed on a Amazon Web Services, which can leverage the scalable cloud infrastructure. So and the backend services are using the Docker to ensure the consistent performance, and the cloud-based deployment architecture can ensure the current platform reliability, but also can support future scalability. And so, and in our current project, we use the previous 24 hours data to predict the next 24-hour data. So I think if so it is not a very long time, very long time series prediction. But if you I think if you want to predict a long time, like the next month or the next years, I think you need to incorporate more the training data. So yes.
Yes, do we answer your questions?
Yes, in some way. I'm thinking more like a work of how many hours you have to put on to build the model. How many, I don't know, monitor you have to install across the campus or something like that to build from scratch.
Yeah, I think we have we have a paper now put it under preprint online. In that one, we detail the step how we do it one by one. Because Wenjing is my first year PhD student. I think she used about one semester putting things together, but during that she certainly has some learning curves back and forth. But now I think if you present her a new campus or new study site, she know much better is how can quickly put things together. We
I see. Yeah.
spend some time
Mm.
looking for the computing resources and the training, right, Wenjin?
Yes, the training process, the training cost, is really depends on your computational resources. If you have lots of high performance GPUs, and you can train the model fastly. Yeah, it depends on your computational resources.
Okay. Yeah. And normally what is the maintenance? This is, I assume it's not like you build it and you're done, right? You have to maintain it. Sometimes probably after 3 months, 6 months, you have to revise the model or something like that. Is that gonna be, could you elaborate on that a little bit?
Yes.
Wenjin,
Yeah,
since
we
now
can.
we can continue to update the data, right?
Great. Yeah. Yes.
Yes. So since it's
Yes, you
yeah,
have to update your training data. Yeah.
Thank you so much. Appreciate it.
thank you. We actually in my team there's another student is working. He's a designer. So now what we are talking about is if the built environment is like this, how it will be, right? So I mentioned that there could be a construction scientist, architecture designer to design the room, remodel the room to see how we can mitigate the overheating stress is indoors and all near the building the green infrastructure nearby your house to bring down the local microclimates. So there's always some other things really enjoyed. My team enjoys to do it through the urban design, architecture design, or even building remodel to see how we can mitigate the stress. Instead of observe how the stress is, we really need through design to remodel. And the design itself, digital twin could be a good sandbox of the design because if you change, you want to see the outcome as quickly as possible, right? So it will become the sandbox for us to test the various building materials and the built environment design.
So could I ask another question?
Mhm.
So I think it's a really good point you raised that that's the whole point of having a digital twin, being that you can make changes in the virtual world and then see, test out the what if scenarios. And so I guess this can be quite complex, right? So I'm wondering about your, do you have like so for these components on this map, for example, buildings, large buildings or small houses, what do you have a model or do you need to work with, for example, civil engineers to incorporate their physics-based models? For example, so large buildings, they have certain designs, and then what are the parameters like the heat dissipated from the building and what goes in? I have no clue. I'm just wondering.
Yes, I do have some very pilot studies with some building information scientists. Their idea is they put for example, they put a sensor in the room. With the sensor capture how many people walk into the room. If you have more people walking in, the air conditioning need to go up, or let's say, or they also need to think about how to clean the air quality. Since the room maybe allow room accommodate more people. If more people come in, certainly the air quality inside will drop. So that's a similar thing is if you are building, we can simulate is because at this moment, we are always saying similarly, hey, this room can only allow 100 people in. But we do not ask whether these 100 people, if all the 100 people, most of them have a health issue, then it might be cause a problem is not because the room cannot hold 100 person. Is you bring 100 people in, the room temperature increase, air quality drops, and those some people with a very serious health problems cannot stay inside. Even I mean, if you put them in meeting for half an hour, maybe we need to call for help. Right. So that is something we have been thinking a lot. Is nowadays in many building size or room requirement is saying we cannot host 10%, or we cannot maximum is 50%. But they do not consider people have different level of response to the stress.
Thank you.
Thank you. Yeah.
I have a comment and a question regarding what you guys have done. First of all, thank you for the great presentation, and it was a very interesting job. And I've been dealing with digital twins, and one thing that I know it's been a practice is that so digital twins cannot be there are multiple, right? So you cannot have a digital twin that covers everything. That's almost impossible mathematically. So the question that I have is that, are you guys taking interoperability and the reusability of your digital twin into consideration? Like following like a specific input structure, or having following I don't know, an output structure or an output model structure architecture. That's a general question that I have. And it would be nice, like I have seen so many digital twins that are once designed, they're really hard to incorporate them to with other digital twins, right? So that's a general comment that I have, and a question that, are you guys following any standards or any specific ideas of how to keep your digital twin connected to the other digital twin?
Great question. First is my philosophy is try to make one digital twin only realize one main function. Building a comprehensive digital twin will cause many problems because uncertainties and or some unexpected repurposing, right? So we might use the digital twin for one purpose, but it might be used in the evil way for other outcomes we totally do not expect. Especially digital twin would like to expose. We are talking about digital replica. So the replica does not mean we will replicate the exact same geometry, because we also need to avoid unnecessary details. For some details, it's totally unnecessary. When you model a specific phenomena, you don't need some. So for that, our philosophy in my team is we have some other digital twins for transportation, some other digital twins for class scheduling. We have also have some ongoing the papers now is preprints and review is how we can use digital twin, allowing us to optimize class scheduling in the real time when we consider a building now is put into a maintenance, or some building the room is flooded, or for some other big events ongoing, we have to cancel the class, or we have to move students from one building to the other building. And for that, even for that, we try to make the digital twin, the function separated from each other. And we use suddenly location will allowing us to hook them, because everything happening in space, and we use location to reference one to the other. But I will try to avoid everything in one digital twin. as I said, it will first make your maintenance very difficult, costly. Anything outdated in one part will first totally decrease our trust on our model. So for each model, I would say is only to a specific purpose. And also, anytime when we use a digital twin, we also try to question ourselves: is using this whether it will someone else will use this digital twin for a very evil purpose or not? So we would rather sacrifice some accuracy, right? Sometimes unnecessary accuracy if it will allowing some thing very bad happens, I would rather to sacrifice this kind of accuracy.
Thank you.
Yeah, and one other thing I would say is we also need to treat the digital twin is another through the mirror is another replica of ourselves in a virtual world. So if we create, I think it's from an ethical purpose. It's kind of you raise if you raise a child, you don't want to, you certainly it's illegal you abandon them, right? Is if you come up digital twin, well, not just think about it in the future to become dead somewhere through there. We need to think about how it can be related to the real world. If real world changes, this kind of digital twin should also be updated. We should maintain, if you have a function, we should maintain that. Otherwise, we spend lots of efforts to building kind of another world of our real world. We don't want in the future, people search the A&M, the campus digital twin, you will find multiple copies, 20 copies. And you have no idea which one is correct, and which one is partially correct, the other one is partially wrong. So in A&M, we have several groups. We work on digital twin relevant things about a building. We also already try our best in A&M to build some digital twin communities, allowing us to communicate with each other, saying, hey, we don't need to replicate. I mean, doing something really reproduce each other, replicate each other. We should work on to find out what we can collaborate, because for those people work on digital twin, they have different expertise. As I said, it's better to make a digital twin more for specific purpose instead of doing everything. So for that, we always will find a spot in the collaboration. Yeah, thank you.
Very interesting. Thank you.
Yeah. So, oh, by the way, when we talk about today, we talk about a campus digital twin. I also mentioned campus is a very specialized built environment type in the urban area, or to be more broadly, you consider that's application of urban digital twin. This Friday, we organize a Zoom with UT Austin because I have another NS project developed with UT Austin, and with them we will build a community of atmospheric and urban digital twin. So because the researchers from UT Austin, they are from meteorology, from weather, climate science.
Very interesting. On this note, so I am working for OGC, Open Geospatial Consortium, and it's I'm not too sure if you guys are aware of us or not. So a recent project.
It's a city is not only a spatial scale. City
yes.
is a kind of, it's vulnerable. We know city is vulnerable, but city is also an innovation engine. So through city, we organize the human society. So that's the reason is I will considering digital twin will become many what if scenarios, sandbox. We let our collective wisdom played in the digital twin to showcase to what other possibility we can have to deal with increasing frequencies of extreme weather.
That's right. That's right. Yeah, no, I was just going to say that there was an activity between, if I'm not wrong, University of Busan in Korea and two other universities in US. I think one was UCS, University of UCS. I can't remember what was the abbreviation for. And the university and another university in Florida. And they did work on the interoperability for urban digital twins. So they come up with how you integrate two different digital twins together and how you can make sure that in future, if you have a different digital twin, you will be able to communicate with them through a way that it's repeatable, right? So I just wanted to highlight that there are similar activities on the interoperability in other universities in US as well. You mentioned University of Austin, right? Texas, is that it? So I just wanted to highlight that maybe you guys should look at those as well and maybe see if there is anything that you can use for your future works on the digital twins.
Yes.
And I 100% agree. A digital twin without a what-if scenario is really not useful, right? We do a digital twin, so we can't do a what-if scenario. Otherwise, why we are doing it anyway? Yeah, that's the comments that I had. Sorry.
Can you share the,
Yes,
the
I
event
also-
link on the chat, please?
Yeah, I put the link. This link is welcome everyone to join our Zoom discussion on Friday. So this is we will also invite a member of National Academy of Science. She Academy of Engineering, Ruby Liang. She will be with us in the discussion. She is also our co-PI in the NS project. For that, we are because Ruby Liang is a leading scientist in atmospheric science, and her work is more like build a large larger region level kind of the atmospheric digital twin. But our argument is how we can meaningfully downscale this kind of atmospheric digital twin to urban city, to neighborhood, or more specifically to a functional zone like a campus. So I would say there is a lot of needs to exchange knowledge because their strengths is mainly on physics-based models. But we will see how the urban is not only a spatial scale. This is kind of because many high density population distribution and high rise buildings, many human-made landscape will make this kind. We know the urban heat island, right? We also know it's a wetland. It's a wetland. Urban wetland is means because of the raining or because of the urban area, it become you have much heavier rain or much slower rain, much fewer rain. So nowadays, this kind of knowledge will allowing us to enable our digital twin to reflect much better about what's a fast growing frequencies of extreme weather. Last but not least, I think there's another great thing we are working on. I also hope we can involve more people to think is how we make a digital twin to talk to digital twin. So in other words, you build a kind of all these digital things. We go to sleep, and these digital twin, whether they can become more autonomous, they can even fix some issues by themselves. And then digital twin, because they are from different tasks of digital twin, but they are all operating in the same campus scale. For example, we have digital twin for maintenance of infrastructure. We have digital twin about building energy. We have digital twin of course schedule. Then task by task, they are different, but all of them serve our campus management needs. Certainly they are related. So how we can set up some mechanism allowing these digital twin can also have dialogue with each other. Yes. Thank you.
Yeah, thank you, Shinye. I think this was great. Yeah, I also posted the link to the notebook Wing Yang created. I think that is good. And she also has like data sets and the publications there. So yeah, for anyone who's interested, might be able to see that as well.
Yes. Thank you.
Any last words before we adjourn? If not, I guess thank you everyone, and
Thank
we'll
you.
see you next week.
Thank you.